Let's welcome Sam.
Yeah, so I'm Sam, I'm from Bristol, and Dima actually gave me a really nice segue into this paper earlier, that question that got asked about VLMs and video contributions. And yeah, essentially, I'm going to talk to you about a really simple idea. We've got VLMs, and we benchmark them with VQA. And in particular, I'm talking about video VLMs, not image ones. And essentially, what I want to know is, how do we quantify how much the video contributes to the output of the VLM? And that is basically what I'm going to try and answer today. So everyone's using VLMs, possibly too much, if you ask me. But they're a pervasive example of multimodal models. The thing is with VLMs, they basically all work in exactly the same way. You have a vision encoder, and you tokenize your video somehow, and then you project those visual tokens to the same space that you can query your LLM with. And your LLM the onus is on the LLM to do much of the processing of the task. And one of the ways that we test how clever VLMs are is using visual question answering, in particular multiple choice visual question answering. But a lot of the progress in the area, as of right now, essentially looks like data sets getting more difficult. They're designed in a manner that is supposedly more difficult to answer the questions. The other thing that's unique to video is that we're just increasing the context length of the video. So we've gone quite quickly from videos being seconds to minutes to now hours, or even longer. But we want to know, are we heading in the right direction, and how can we quantify this? So I'm going to pose a question to the room. If you've got this question here, that's asking what the primary purpose of a cup of water is in a video and how it contributes to this painting process. I'm going to show you two frames. So you've got one frame here, hopefully you can see it. The person is kind of painting with a paintbrush. Or the second frame, they're actually dipping their paintbrush into the water. Right, so if you think this frame is more useful for answering that question, raise your hand. Good. If you think if you think this frame is more useful for answering that question, raise your hand. Okay, right, yeah. We're all making sense today. So I'm not going to answer that question yet, because we're going to use Shapley values to determine which of these frames is more important. So now, you might...
Isn't there a third one that none of them, like just from the question you can answer?
This is a separate issue with, in particular, ego schema. But yeah, this is valid. If you ignore the fact that the question is answerable through text, one of the frames is more important, yeah. So yeah, the method of feature attribution we're going to use is, they're called Shapley values, and they're from game theory. Don't worry if you're not familiar with them. Essentially, when you calculate Shapley values, you assign all of your features a signed contribution, a positive or negative value. And this tells you, basically, how much a feature contributes towards the output of a model. And it's nice because it's independent of accuracy. Accuracy, it only really tells you information about the class that wins, rather than all of the classes and how they kind of change in the model. So if you've got three features here represented by these dots, all you do is you mask out all of your features, and then you measure the change in your output logits when you add the features back in all of the possible orders that you can add them back in. Now, obviously, this is a high price to pay. In the formula here, we can see we're asking for all possible permutations of your input features, which is intractable, especially with VLMs. So we approximate this by subsampling the total number, subsampling from all of the set of permutations, and you approximate the Shapley value, and the more permutations you use, the more accurate your Shapley values are. So I'm just going to skip straight to the output that you receive when you calculate your Shapley values. So if you've got your input to your VLM, you've got your video. Here it's only 3 frames, but that's just an example. You've got a question, and you've got your multiple choice answers. You get a Shapley value for all of your features, so this signed value. Here, we only really care about the magnitude. We only care about how far the feature pushes the logic rather than the direction. So we're going to take the absolute value. Now, how can we use these to calculate modality contributions? So as you can see, I've color-coded the input modalities. You might ask why the question and the answer are separated because they're both textual. We did this because the purpose of question and answer in multiple choice, they're kind of distinct and separate. If you completely remove your answers, it means something very different to completely removing your question. So you've got 3 modalities here, and the contribution of each modality can be quite simply calculated when you just sum the Shapley values within the modality, and then you look at the ratio between these sums. Which, fine, okay, so if video has a contribution of 0.3, then it's contributing 30% of the total towards the logic, basically. But video in particular is special because it's kind of unbounded in length. And so you might say if the modality increases, then video is just going to explode eventually. So we also look at, instead of summing these values, we take the mean. So this is kind of the average contribution of each feature within the modality. So what do these look like? If we look at the modality contribution, the whole modality, for a set of data sets, things look sort of balanced. This is not too crazy, but things change a lot when we look at the average feature contributions, particularly for video. The balance changes considerably, and the order is now always video is less than question is less than answer. So we tested this for a few different models and a few different data sets. So here, all you need to know is that red means there's less contribution, and blue means there's more contribution. So if you look at the video columns, they're almost all red. And even in the case of Video Llama 3, which has relatively high contributions from the entire modality, when you go to the per feature contribution, it's like less than 10%. So each frame is contributing very little towards the output when you compare to the textual features. And the second thing I want to draw your attention to is the fact that the question features are almost always contributing less than the answer features. I don't know if this really makes sense when we're asking models questions, not just like matching videos to text, basically. So now we can return to the question that I posed to you. It's actually the one on the left if you look at the Shapley values. So let's have a look at this question. So here, blue is instead a positive contribution and red is a negative contribution. So that left frame is actually the frame out of all 180 input frames that contributes most positively towards the answer of this question, which does not make much sense to me. And the frame on the right of the person interacting with the glass of water actually contributes negatively here, which makes even less sense. And even worse, I think this frame, the person is also interacting with the glass of water, is also negative here as well. So the model basically just does not care about the keyframes of this video when answering the question. Obviously, part of that is because of the textual bias in terms of how easy it is to answer. And also, the model does get this question correct. So I want you to think about when you've done multiple choice exams before in university or school, you almost always only have 4 or 5 choices. This is just like the standard. This is how we do it. We've arbitrarily decided that this is enough for VQA datasets as well, which is probably because good negatives are really hard to create, as we know, and it just makes sense to do it the same way as you formulate questions in real life. But we just wanted to add on a bit of an addendum here. What happens if we just add trivial negatives from other questions in the data set that we know are false, way past 5, so up to like 25, and then recalculate the Shapley values and see if things change. So here, we've got the average feature contributions for video, question and answer, and then the accuracy when answering the new benchmark. And essentially, what you need to look at here is the video contributions go up, so each individual frame is starting to contribute more, and you get the same effect for question. It's actually more of an effect for question. The words in the question are now more important than the words in the answer, and the answer contributions drop. And the other nice thing is that the data set sort of becomes more difficult as a result of this, even though a human is not going to find this any more challenging. There's just more bad negatives to sort through. So yeah. So what are the takeaways? So VLMs, they're not blind to video. They're using it somehow, but they are often primarily steered by text, which might be fine in principle, you could argue, if the keyframes are well attended to. But as we've seen, often enough, they don't make sense. And we've also seen that adding trivial negatives to kind of expand the space of multiple choice VQA can increase the contribution of the other modalities. But basically, my message here is multiple choice VQA is limited in evaluating the understanding of VLMs. And I'm kind of more interested in opening a discussion on whether language modeling really belongs in computer vision to this degree, and especially like video modeling. I think this is kind of an open problem that is only going to get worse as we use language models even more to solve these problems. But yeah, so we've released this paper on arXiv recently, and the code is all released, so feel free to have a look. But yeah, that's me done.
Thank you very much. Because you were saying basically that, oh, it doesn't look at the videos, or not as much as we would hope, right? But then language, there's a lot of context there, and obviously a lot of these models have been trained with a lot of. So when you said, oh, why is the water, what's the purpose of the water? I immediately thought, okay, it's going to be to clean the thing. But if instead in the video someone was drinking, let's say, the water because the painter was very thirsty, I don't know. Basically my question is this the correct data set to evaluate this, or is there a more niche sort of way, if we have a video that does not produce something we would expect it to, that would not be something that could be in a language setting, like in a, someone who's written a blog about this or something. Would that be a better setting to evaluate
So like if there's like red herrings designed to catch out the language model. I think so. I think that would be interesting to look at. Yeah. I think, so like we have another example here where David Blaine is pulling a card out of his mouth, right? And the answer is the Jack of Spades. The model just does not even look at the frame that contains the Jack of Spades. So this is kind of one where you can answer it from the text. It's like you actually have to see at least one frame in the video to answer the question. And even in this case, it's kind of ignoring this. So I think that's an aspect of it, yeah, that definitely could be explored. But yeah, part of the issue is I think VQA datasets are asking they're asking about things that appear in the video. It's like kind of like a caption of the video in a sense, just kind of turned into a question answer tuple. But yeah.
Thanks.
I have one last question.
Thanks for the talk. I have had similar reservation, but you quantified it, so thanks a lot.
Yeah.
So I feel like a lot of VQA benchmarks ask very leading questions, and the answers are leading, which is what you found out. So have you tested like opposite things, like the video is showing something else and the answer questions are leading towards something else? And is it testing? And also, are these observations consistent across all the VQA models that are there, or is it like is there some aspect of like how they are tokenizing and things like that actually are affecting how they're looking at it?
Yeah, generally across models, things seem to look the same regardless. We treated the models as like black boxes. However the model tokenizes text and video, we kept it the same. I think it sort of gets worse as the context length increases, actually. I think because some of these data sets, like LV Bench in particular, it's like an hour-long input. So you take an hour-long video at like less than 1 FPS or something, and essentially you're trying to spot something that can be answered like from one frame amongst that 50 minutes, 60 minutes. So yeah, the video is long, but I think the question is, are we really asking like sensible computer vision questions from these videos? I don't think we are necessarily.
Cool. Thanks a lot.
Thank you.
I think that's the end of this whole season. If any more,